alternating series. This is, well, we're going to define it. Alright, we're going to use the alternating series test to determine whether an infinite series converges, of course. This is the first one where there's an actual error approximation, so we know how far off we are in our approximation. Generally speaking, alternating series, you can't, well, for some of them you can't find the actual sum, but we can approximate it, and with the alternating series remainder, we can approximate how far off we are. We're also going to classify a convergent series as absolutely or conditionally convergent. And here, the last bullet, we can rearrange an infinite series to obtain a different sum. What that means is when you have an infinite number of terms, which order in which you add the numbers actually matter, right? In a finite sequence of addition, order doesn't matter. You can change 2 plus 3 equals 3 plus 2. But when you have an infinite number of them, then the sum can change. But we're not going to do that. If you want to see that explained, I will gladly do that in class, but I'm not going to take the time for it in the video. Okay. In fact, in this video, we're only doing the first bullet, using the alternate series test to determine whether an infinite series converges. All right. First of all, what's an alternating series? Either the even terms are negative or the odd terms are negative. So it can't do like positive, negative, negative, positive, negative, negative, positive. It can't have that weird pattern. It's got to be positive, negative, positive, negative, positive, negative, positive, negative. Okay. All right. So, and this is the alternating series test. So you either have this version, this is the odd ones are negative, or you have the second version, this is where the even ones are negative. And then there's two conditions. The terms without the negative signs have to go to 0, which is normal, right? And term test for divergence says if it doesn't equal 0, then it doesn't converge, right? And this other condition that each successive member of the sequence is smaller than the previous one. It has to be steadily declined. It steadily go down. All right. All right. So there's really 3 conditions. It's got to be an alternating series, and then those 2. Okay. All right. So let's get started. Here's the first example. All right. So remember, this 1 over n by itself is the harmonic series, but we're going to make it an alternating series by adding this negative 1 to the n plus 1 power. So it is an alternating series simply because of that. And we know the terms go to 0. As n goes to infinity, 1 over n will go to 0. So it passes the first condition. The second condition is this. This is actually pretty straightforward. A sub n plus 1 is 1 over n plus 1. And that's obviously, and it should be obvious by now, that this 1 over n plus 1 is smaller than 1 over n whenever the denominator is obviously bigger than the denominator of another fraction. Then the fraction itself is smaller, right? It's the exact opposite. Okay, so here we go. So it passes the second condition. So by the alternating series test, this series converges. Second example. All right, this is ugly. All right, so we're going to separate the negative from the actual 2. Right? When we do that, it looks like this. Let's look at the first condition. Right? If we just look at this term, we're ignoring the negative. As n goes to infinity, remember the power, an exponential function would overpower any polynomial, so the limit is 0. And if you don't remember that, you can always use L'Hopital's rule, right? Here you have infinity over infinity. That's an indeterminate form. If you take the derivative numerator, it would be 1. The derivative denominator will be 2 to the n minus 1 times the natural log of 2. So the 2 to the n doesn't go away. So yeah, the limit is 0. Second condition. Okay. This is the painful part of this problem. How do you show that each successive one is smaller than the other? Okay. So there's this really weird way of doing this. This is the author's way. There might be another way, such as taking the derivative. Okay. All right. But if you want to see it done the other way, you can ask me in class. I'm doing this the way the book does it. Right? So 1/2 is less than or equal to n over n plus 1. Just think of this, for n greater than or equal to 1. So 1 over 2. If n equals 2, that would be 2/3, right? If n equals 7, that would be 7/8. So yeah, 1/2 is less than any of those values. All right, now there is a clever way to write 1/2. Right? We can write 1/2 in this form: 2 to the n minus 1 over 2 to the n. In other words, the difference between these, the numerator and denominator, is just a factor of 2. Example, like 1/2 is equal to 2/4. Right? 2 is 2 to the first, 4 is 2 to the second. How about 16/32? Right? That's 1/2. 16/32 is 1/2. 16 is 2 to the 4th. 32 is 2 to the 5th. Right? All right. So that's a clever way to write. And so what we do? So I'm going to look at this version of 1/2. Right? I've rewritten 1/2 as 2 to the n minus 1 over 2 to the n. Now we're going to grow. Okay. In geometry, way back, right, several years ago for some of you, there's this rule that if you have a proportion, that you can switch these two values, right? You can switch the extremes, or you can switch the means. If you don't remember what that means, don't worry about it. It's the opposite corners of a proportion. So I'm switching the 2 to the n minus 1 and n plus 1. And because all these values are positive, it doesn't affect the inequality sign. All right. So n plus 1 and 2n minus 1, I have switched them. Right? By the way, you can do it the long way. The book does it the long way. You multiply both sides and then you divide, blah, 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 blah. All right. So what is this, though? What is this expression? Well, that's a sub n plus 1. Right? If you plug in n plus 1 into this expression, right, numerator becomes n plus 1. N plus 1 minus 1, the ones cancel and you get this 2 to the n. So that's the a sub n plus 1. And of course, this is the a sub n version. That's the normal version, right? We're just ignoring the negative for now. All right. So that means this is true. Since the original is true, then this is true. All right. So it has passed the second condition. Therefore, by the alternating series test, this series also converges. Okay. When does the alternating series test not apply? All right. So here's one. What do we got here? Okay. Okay, the first term is 2. The second term is 1.5. Next term is 1.3, 1.2, 1.16. So yeah, so these terms are steadily going down. So that means it's passing the second condition, right? That each successive term is smaller than the previous one. However, it fails the first condition. Look at that. N plus 1 over n. That limit is 1. It's not 0. So this really fails the nth term test for divergence. Sorry. So you could have just said, oh, whatever. Nth term test for divergence. Nth term test for divergence. It's not equal. The limit's not equal to 1, so it doesn't converge. So this is divergence. All right. All right. Here's another example. Okay, this is kind of weird. First condition. The terms are going to 0, right? So this is 2, then 1, and then 1, then 1/2. It goes up, but it goes down, and then, but it's 1/3. It's going to 0. It's going to 0. It passes the first condition, and the second condition, however, this is not true. That's not happening. Okay, let's talk about it again. So it's 2, and then 1, and then 1. It's equal. It's okay to be equal. All right. And then it goes to 1/2, but then it goes up to 2/3. And remember, we're ignoring the negative sign, right? Whenever you do this comparison, you're ignoring the negative sign. So it went from 1/2 to 2/3. And then it goes down to 1/3. And then it goes up to 1/2. 2/4 is 1/2. Right? And then it goes down to 1/4. And then it's probably going to go up to like 3/5 or something like that. Okay? So the idea here is that this second condition fails, so the alternating series test does not apply. All right. Now, you might think, so what do we know about this series? Well, if you actually add them together, right? If you actually add this is 1, this is 1/2. So I'm adding every other term, right? So I'm taking the negative step and adding it to the positive step. So the negative step and the positive step is 1. Negative step and positive step is 1/2. Negative step, positive step is 1/3. Negative step, so look, it's going 1, 1/2, 1/3, 1/4, 1/5. What series is that? Well, that's the harmonic series, so it diverges. Okay. So yeah, this is the whole idea behind rearranging the order. So this time I'm actually grouping terms together, and when I group these terms together, it turns into a harmonic series. So it diverges. So in this video, we covered the alternating series test. We saw some weird things happening, but well, Don't worry, you won't be held responsible for the weird stuff. Okay. We learned series like the harmonic series can converge if we turn it into an alternating series. So that's the weird part about this. So whenever you have sign changing back and forth, it actually makes it cancel itself easier. So that's why an alternating series converges more often than a regular series. Okay. All right. So that's it. There is a second video. Make sure you watch that because this section is a longer section than the other ones. All right. Talk to you later.